So in this video, we'd like to look at another property of the characteristic polynomial of M. And please recall that the characteristic polynomial in this case should be a polynomial of degree n. So let's say you're able to find the characteristic polynomial of such a matrix M. We would like to get more special properties depending on the polynomial of M. And first, please do the following step. For example, think of this as an equation you have. If you replace lambda by 0, can you see what happens? If you set lambda as the variable to be 0, the left-hand side is going to be 0 minus matrix M, right? And the right-hand side is going to be, you see, all the term now is 0, basically. From the first term to the second last term, the only non-zero term is probably the constant term, right? So it means what? It means determinant of minus m is gonna be the constant term in the characteristic polynomial. And please recall this case. Actually, the fact is, this determinant is the same as minus 1 because of this constant to the power n times the determinant of m. This is the same as the constant term Cn. And I hope you recall this fact, right? This is a fact we have described already for the property of the determinant. If you look at the scalar multiplication of matrix M, and actually the determinant of k times M is the same as k to the power n times determinant of M. And n is basically the number of rows or the number of columns of the matrix M. And that's why you're arriving at this step from the second last step, and please keep this equation in your mind. Let's call this equation single star, and I would like to look at the second equation now. For example, if you're able to factorize the characteristic polynomial in this way. So please look at the current equation. I'm not claiming that all the eigenvalues are distinct. Some of them may be the same. So in that case, it means the eigenvalue is repeated. It has multiplicity higher than 1. And let's now try to set lambda be 0 now on both ends, left and right. Please look at the left-hand side. If you set lambda be 0, you see all of these are 0, right? It means the left-hand side is left with the constant term Cn. And how about the right-hand side? If you set lambda be 0, can you see what happens? Basically, it means the first term in the bracket is going to be minus lambda 1. The second term is going to be minus lambda 2, right? And until the end, the last term, which is minus lambda subscript n. And you see there are basically n copies of minus 1. So basically I can write it as minus 1 to the power n times the product of all eigenvalues together, right? And let's look at this equation as a double star. Now, please compare the two equations you have, the single star and the double star. Can you give some conclusions based on these two? So you see now the fact is that I'm just combining the two equations together because this term is the same. So I can use the left-hand side with this, and the right-hand side is going to be minus 1 to the power n times the product of all eigenvalues. And of course, this factor can be cancelled. So it means what? It means basically, surprisingly speaking, the determinant of a matrix M is actually the same as the product of all the eigenvalues, right? So I write it as a property here. So it's quite an interesting fact that connects the determinant of a matrix M with the eigenvalues of that particular matrix. And then the second property based on this is that, so if you forget about this fact, and please go back to the video about the properties of determinant. The fact is, if M is invertible, it is equivalent to the fact that the determinant of the matrix is non-zero. These two facts are equivalent. And can you give me some new conclusion based on this black box you just have seen? You see, determinant of M is non-zero basically is equivalent to the fact that you multiply all the eigenvalues together. It should be non-zero, right? And it means what? It means that if M is invertible, it is equivalent to the fact that all the eigenvalues are non-zero, right? Or the other way to say it, if M is not invertible, it is equivalent to the fact that if you take the product of all the eigenvalues, it's going to be 0. It means at least one of the eigenvalue is 0. So you can look at all these connections between the invertibility of a matrix M, the determinant of the matrix M, and also the set of eigenvalues of M. And let's look at an example now. Please look at the current problem. I'm not giving you the matrix M. I'm only giving you the characteristic polynomial of the matrix M. And can you give me some properties of the matrix M based on that? So the question I would like to ask in the first one is whether the matrix M is invertible or not. And based on what we have just said, if M is invertible, it means all the eigenvalues are non-zero. That's why when you multiply them together, the product of all eigenvalues is non-zero. And please look at all the eigenvalues here. So we can make the polynomial here 0 and solve for this. I trust that you're able to solve such a polynomial now. So you see clearly now you have three distinct eigenvalues, 0, -1, and -2. And then, because of the fact that one of the eigenvalue is 0, and based on what we have said in the last page, we understand that M is not invertible because of the fact that when you multiply all the eigenvalue together, it's gonna be 0, right? And let's look at the next problem B. So the problem B is different. I'm asking you whether the M is diagonalizable, and it depends on your knowledge on this topic, and we have described something about that in a couple of videos earlier already. Diagonalizable matrix M basically means M is similar to certain matrix D. And once again, this property is in some sense very closely related to the eigenvalues and the eigenvectors of the matrix M. And because M now is 3 by 3, and also M has three different eigenvalues, right? And different in the sense that we automatically understand it must have three linearly independent eigenvectors. Basically, one eigenvector for each eigenvalue, and for the eigenvectors associated to different eigenvalues, we understood it already that they must be independent of each other. And this fact implies that the eigenspace of M is actually 3, right? So I'm talking about the dimension is actually 3. And this fact is good to imply that M is actually diagonalizable. Actually, D has the property that all the diagonal entries are simply the eigenvalues of the matrix M. And anyway, we don't have to do a lot here. We just have to confirm that the answer is actually yes to this problem. And M is actually diagonalizable. And that's the end of this video.